Welcome. My name is Ahmed Ibrahim. Today I'm presenting our research on a critical intersection in artificial intelligence, which is knowledge graphs and large language models. We are looking at how to build systems that are not intelligent but also equitable and sustainable. Let us start with knowledge graphs. Knowledge graphs provide structured, precise, and domain specific knowledge, represented as graphs or a structure form. On the other hand, we have large language models that offer human like reasoning and flexibility. When you combine them into a single system, we create an artificial intelligence that can reason over complex structured data with natural language capabilities. We can carry out this process in two ways. As shown in the diagram, the first approach is using large language models to construct knowledge graphs, which involves generating new graphs from raw text. And the second approach is inferring missing links in an existing knowledge graph. The problem here is that our graph architect, which is the large language model, was trained on a big chunk of internet resources, a place full of human hallucinations, historical gaps, and systematic inequalities. Because large language models reflect their training data, they carry inherent biases, such as racial, gender based, and ideological bias. Today's talk is about what happens when those biases enter our knowledge graphs. This brings us to the core challenge. As we have seen, large language models allow us to expand knowledge graphs at incredible scale by automating generating entities, relations, and attributes. However, this process is entirely model independent. The danger is that bias or even simple noise in the source data becomes encoded directly into the knowledge graph. When this happens, it is propagated to downstream decision systems. It feels like an objective source of trust. In reality, it may just be a systematic, unfair pattern dressed up as a fact. We aren't just passing on information, we are passing on a frozen version of human hallucination. To understand why this is such a systematic threat for our intelligent systems, we need to distinguish bias from a simple mistake. Bias is not just a random error or a technical glitch, it is a patterned skew. Look at the research by John Polonmuili, where we examine facial recognition systems from major tech giants. The errors aren't distributed evenly. There's a massive gap in accuracy specifically. Higher errors rate for darker skinned females. This is the definition of systematic bias. The system works well for some but fails predictably for others. In the context of large language model augmented knowledge graphs, this same logic applies. If our architect, which in our case here the large language model, carries these patterns, skews, they do not just produce noise data, they produce distorted knowledge. This bias isn't just temporary lapse in judgment by the large language model, it is encoded directly into the knowledge graph that we try to build. We are essentially taking a systematic social hallucination and hard coding it into our digital infrastructure, leading to inherently unfair outcomes. Now, let us look specifically at the knowledge graph itself. We often assume that because the graph is being built with some kind of specialized people, we assume it is neutral. But as this visual shows, should not be assumed neutral by design. A knowledge graph is only as good as the domain data we select for it. If our selection is skewed, our graph will be also skewed. Furthermore, the ontology is often encoded rigid or limited worldviews. A common example is gender. If any ontology only allows for binary classification, it inherently erases the complexity of the real world. As you can see in the diagram, this leads to a center versus periphery problem. We can easily observe entities overrepresented sitting at the heart of the graph with massive connectivity. As you can see here in the graph, the red node. Meanwhile, marginalized groups, or niche data points are either weakly connected or missing entirely from the graph. The takeaway here is that every knowledge graph reflects the limitations of its data and the design choices of its creators. When we use a large language model to build these graphs, we are often automating and scaling these very imbalances. So, how does this bias travel and grows within a system? We break down bias propagation into three distinct mechanisms, as shown in the diagram on the right. First is direct propagation. This is straightforward path. The bias flows from the training data to the large language models and directly into the knowledge graph. The second is indirect propagation. Here, bias creeps in during intermediate tasks. They vary. The very process of extracting and linking is where the large language models might make stereotyped assumptions. Third and most dangerous one is reinforcement propagation. Look at the arrow between the knowledge graph and the applications at the bottom of the diagram. This creates a feedback loop. If an automated hiring system favors certain profiles, those candidates get selected. New hires then generates more data, which is fed back into the system to update the knowledge graph. The system looks at these are the successful profiles. The loop closes, the patterns repeats, and the bias increases exponentially. This is why passive observation is not enough. Without intervention, the system automatically makes itself more biased over time. Before we discuss how to fix these issues, we must acknowledge that if this were easy, it would already been solved. Mitigating bias in large language models augmented knowledge graphs presents four significant challenges. First, fairness. Fairness is a moving target. It isn't a fixed mathematical constant. What is considered fair is a healthcare diagnosis graph is very different from what is fair in movie recommendation systems. It varies across domains. Second, we face a trade off. As a target icon suggests, effort to restrict or debias a model often impact its accuracy and utility. If we over sanitize the architect, in our case here the large language model, the resulting graph might become less detailed or lose its reasoning power. Third, there is a computational cost. Migration strategies such as retraining models or conducting massive graphs audits are increasingly resource intensive. This ties back to our goal of sustainable AI. We have to find ways to be fair without consuming an unsustainable amount of energy. Finally, there is an audit challenge. In these complex pipelines, bias is difficult to trace. When a biased output happens, is it because of the training data, the extraction prompt, or other graph structure itself? Finding the root cause in this web is a massive technical hurdle. To overcome the challenge I just described, we cannot rely on single fix. Instead, we propose a multi-layer framework. As you can see here in this pipeline, bias mitigation requires coordinated intervention at every stage. First, at the input data stage, we audit the raw materials. This involves rebalancing datasets and use data augmentation to ensure that the foundation isn't skewed before the large language model even see it. Second, at the large language model stage, we refine the architect directly. We apply fairness constraints and adversarial debiasing to teach the model to ignore stereotypical patterns during its reasoning process. Third, at the knowledge graph stage, we focus on the blueprint. We use intentional schema design and the graph completion techniques to ensure that marginalized entities aren't left in the periphery we discussed earlier. Finally, at the output stage, this is a final inspection. We use automated metrics and scheduled human audits to catch any bias that slipped through the early layers. By intervening at every step, we ensure that the final product is not just large language model augmented graph, but a fair and equitable one. Of course, we cannot improve what we cannot measure. Evaluation is the cornerstone of our research, and as this slide shows, we must balance two distinct goals: correctness and fairness. On the left, we look at quality metrics before the data even enters the knowledge graph. We use tools like Blue and Rouge to check for surface similarity and BERT score to ensure semantic accuracy. This tells us if the architect or the large language model in our case is being precise. On the right, we move into bias specific and knowledge graph level metrics. We use established tests like wheat and seed to measure stereotypical associations. More importantly, we look at representations balance mathematically, checking if different groups are represented with equal connectivity and coverage within the graph structure. We test these against benchmark datasets like cross pairs and stereoset. The ultimate goal here is to ensure that our graph is not just a high quality piece of engineering, but an ethically sound one. A graph can be technically perfect, but still lead you to a wrong destination if it is built on a biased foundation. As we move toward a conclusion, let us revisit the most critical lessons from our research. First, we must acknowledge that the double edged sword large language models are an incredible engine for scaling knowledge, but they are an imperfect architect for large language models. They naturally introduce bias into the construction process. Second, this bias is pervasive. It doesn't just live in the raw materials of the data or the engine of the model. It becomes hard coded into the very structure of our knowledge graph. Third, remember the feedback loop. Without intervention, bias propagates and amplifies. A small skew in the foundation today can become a massive injustice in a real world application for tomorrow. This is why we advocate for end to end intervention. We cannot just fix the input and hope for the best. We must monitor the graph as well as the final output. Finally, our goal is a system where fairness and quality are in a perfect balance. We shouldn't have to choose between a smart system and a fair one. However, the work is far from over. Our research also highlights the significant hurdle that remains for AI community. The biggest challenge is that there is still no standard definition for fairness that works across every domain. What is equitable in a clinical healthcare graph might look very different in a legal knowledge base. Furthermore, while we have good tools for measuring large language models, we have limited benchmarks, specifically for knowledge graph level bias. We need more ways to mathematically prove that a graph's structure is representative. We must also be honest about the trade offs. As we move toward more equitable systems, we often see a tension between fairness and performance. Building sustainable AI means finding the sweet spot where we aren't sacrificing the system's utility for the sake of its ethics. Finally, real world deployment and monitoring remains difficult. Bias is a moving target. As world views shift and data changes, our digital community will require constant inspection and accountability. Thank you so much for listening to my presentation. And to wrap up our journey for the knowledge graphs, our research is ultimately a call for accountability. As we continue to integrate large language models into our digital infrastructure, we must ensure that we aren't letting a biased architect or a large language model build the foundation that our society will rely on for life alerting decisions in healthcare, law, and credits, for example. By adopting the holistic end to end framework we have discussed today, we move away from black box systems and toward AI that is not just intelligent and scalable, but truly sustainable, equitable, and fair. Thank you for your time and for your attention. My contacts information is on the screen, and I would be happy to take any questions you might have. Thank you.